we're going to do an algebra review. The first task is to determine a numerical value for x given the following equation. The first step would be to rearrange the equation such that x is on one side of the equation by itself. We can get x by itself on the left-hand side if we divide it by 17.9. That means that 17.9 cancels out. In algebra, whatever we do to one side of the equation, we have to do to the other side of the equation. That ensures that the equation remains true. So we need to divide the right-hand side of the equation by 17.9. For clarity, I'm going to rewrite the equation. The equation now is that x is equal to 63.5 divided by 17.9. If we put these values into our calculator, we'd see that x is equal to 3.547486. This value is what we're going to call the calculator answer. However, we're not done with this problem. These numbers are measured number, so we need to consider how many significant figures are appropriate to express in our answer. As we've learned, when we count the number of significant figures in a measured number, all the digits 1 to 9 are going to be significant. We look at our numbers that lead into the final result. We see a measured number. All three of these digits are 1 to 9, so they all count. And therefore, we have 3 Sig Figs in the numerator. In the denominator, we also have 3 digits, all 1 to 9. So all of them count as significant. We have 3 Sig Figs in the denominator. This tells us that we can express our final answer to 3 Sig Figs. We apply that to our result. We see we have to stop after 3 digits. We look at the first number to be dropped. It's greater than 5, so we round up. That means we add 1 to the preceding decimal column, and our final answer is appropriately expressed as 3.55. Question 2. We solve for a by rearranging the equation so that a is by itself on one side. To do that, we multiply the left-hand side by 9.86, and therefore that cancels out. But we also have to multiply by 9.86 on the right-hand side. For clarity, I've rewritten the equation and given the calculator answer. Now we need to determine Sig Figs. We again apply the rule that all numbers 1 to 9 are significant. So we have 2 Sig Figs in the numerator here, 3, and 3 in this number. This problem involves multiplication and division, and the rule is that we count Sig Figs and we use the lowest number of Sig Figs of the numbers that are leading into the result when we report the answer. That means we can only use 2 Sig Figs in our final answer. We count 1, 2. The first number to be dropped is less than 5, so we just drop all the rest of the digits. And our final correctly reported answer is 14. To solve for b, we first subtract 18.2 from each side of the equation. So we know that b is equal to 54.3 minus 18.22. Our calculator answer is 36.08. Now we determine the Sig Figs. When considering problems involving addition and subtraction, when we're looking at Sig Figs, we count decimal places. This is what it means. When we look at these numbers, we see this first number is expressed out to the tenths place. The second number has more precision. It goes all the way out to the hundredths place. For this result, we cannot go beyond the tenths place. It's because for this number here, we don't know what that value is in the hundredths place. We're limited to go to 1 decimal place. 1 decimal place. Let's look at our calculator result. We have to limit that to 1 decimal place. The first number we drop is greater than 5, which means we round up. We add 1 to the preceding decimal column. And our appropriately expressed final answer is 36.1. In question 4, to get y by itself, we need to both multiply by 5.7 and divide by the product of 11 times 1.01. That allows us to get y by itself, but we have to do the same thing to the other side of the equation. So we need to multiply by 5.7 and divide by the product of 11 times 1.01. I've rewritten the equation and the calculator answer. Now we need to worry about Sig Figs. The Sig Fig rule in multiplication division is that we count Sig Figs. So we have 3 Sig Figs, 3 Sig Figs, 2 Sig Figs. All of these numbers have only digits 1 to 9, so they all count as significant. Looking at this number here, we see we have a 0. Zeros may or may not be significant. This 0 is significant because it is a captive 0. It has non-zero digits on either side. So this number has 3 Sig Figs. Our final answer is reported to the same number of Sig Figs as our worst measurement, which has the least number of Sig Figs. 2 Sig Figs here. So we're limited to 2 Sig Figs. We look at the first number to be dropped. It's less than 5, so we just drop all of the remaining numbers. So our final correctly reported result is 49. Determining the Sig Figs in some numbers. We remember that all the digits 1 to 9 are always significant. The only question comes to the zeros. We look at the number 25.301. This has 5 Sig Figs. The 2, 5, 3, and 1 count as significant. This 0 is a captive 0, which we see is significant. In B, we see some zeros that are leading zeros, and they do not count. They're not significant. These captive zeros are significant. When we look at trailing zeros, we look to see whether or not there's a decimal point in a number. This number has a decimal point in it, so these trailing zeros are significant. We count our Sig Figs, starting with a 9. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 Sig Figs in this number. In C, we have an ambiguous number of Sig Figs. We have trailing zeros that are in a number without a decimal point. Again, when we look at trailing zeros, we note whether or not there's a decimal point in a number, in which case they're going to count, or if there's no decimal point in a number, in which case our Sig Figs are ambiguous. In the next problem, we see that we have non-zero digits that are all going to count, and we have captive zeros. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 Sig Figs. 708 is another example of a number with captive zeros. Captive zeros count as significant. So this number has 3 Sig Figs. In F, again we have trailing zeros. However, this number contains decimal point. So the trailing zeros count as significant, and all of these captive zeros count as significant. So when we count them, we have 3, 6, 9, 12, 14 Sig Figs. Now in chemistry, we almost never come up with numbers containing 14 Sig Figs, but we can handle it.